Magnetic field starts with a recap of the classical equations. So let us remind ourselves what those equations are. They are the famous Maxwell's equations. So the curl of the electric field is equal to minus the time derivative of the B field. And this is the famous Faraday's law. And there is an analogous law for magnetic fields and the time derivative of electric field. And this is Ampere's law. With Maxwell's correction to it. And then Gauss's law tells us that the divergence of the electric field is proportional to the charge density. We derive the famous Coulomb's law from this equation. And a statement that there is no such thing as a magnetic monopole. If we ever discover magnetic monopoles, we'll have to change the right-hand side and rename this equation Dirac's law. So, as you know, and it's a famous fact that these four equations, when combined, admit electromagnetic waves as their solution. And that electromagnetic waves electromagnetic waves have two polarizations, or sometimes called degrees of freedom, which will be important for us today. Another famous fact about these equations is that they are Lorentz covariant. Under a Lorentz transformation, what we call an electric field and what we call a magnetic field, they mix. In fact, there's a really wonderful textbook on electromagnetism by Purcell, where he assumes right off the bat that electromagnetism is Lorentz invariant or Lorentz covariant, and then from the observations of electric fields and marrying it with Lorentz transformation, he derives magnetism as a consequence. Okay? So we can write these equations in a covariant form, and this is something I think you saw in how that arises in one of the tutorials of relativity, the first relativity tutorial. So for the covariant formulation, you introduce an antisymmetric field strength. So this is a field strength. And let me write it as a matrix. So the mu nu are labels, columns, and rows. And it's antisymmetric, so it means that the diagonal elements are 0. And the first row contains the electric field components. And the magnetic field components sit like so. That should be B3. Should be B1. Right. In other words, the 0I component are given by the electric fields. The IJ components are related to the magnetic field components by the Levi-Civita tensor in 3D. So to write in the covariant form, we also have to introduce a covariant source. So we define a 4-dimensional vector whose 0th component is the electric charge, and the 3 components are the 3-vector current. Then the then the Maxwell's equations, which contain sources, so that would be Ampere's law and Gauss's law. Those two can be written in this covariant form. Note that since F mu nu is antisymmetric, that means, so this implies if we contract a derivative with respect to x nu and contract it with this guy, then because partial derivatives commute, the left-hand side will vanish, right? Because partial derivatives commute, and this anti-commutes. So this is antisymmetric. So this will give you 0, which implies that the consistent source that you need for this equation is a conserved current. The other two Maxwell's equations, the one without sources, those are sometimes this is written in the form language as exterior derivative of f equals to 0. Because f is antisymmetric in mu nu, you can write this as right. So we will be interested in an alternative form of these equations. So we will be which will involve a 4-dimensional vector potential, which is traditionally denoted by A mu. And A mu is defined in the following way. It is the potential on which from which you derive the Maxwell's field strength. In form language, this is written in this form. So what do you gain by by introducing the vector potential? The Maxwell's equation with sources then become, is box. This is the D'Alembert. which is the generalization of the Laplacian that includes the time direction. So Maxwell's equation with sources become this equation. The other equation, number 2 over there, that becomes an identity. That is no longer has dynamical content in terms of A. Because if you plug in the expression for F in that first equation, what you have is you're antisymmetrizing these indices, but since partial derivatives commute, you're antisymmetrizing two objects which are symmetric, and therefore it is 0 by definition. So in form language, this is written as d squared of A is 0. And if you know any differential form, you know that this is an identity. So why do we need A mu? Now why do we need these guys? In classical electromagnetic theory, this is a luxury. You don't really need this. You can always work with E and B. But when you're doing quantum mechanics, this is essential. Examples. So for quantization, we actually need the gauge potential. But let me motivate it by giving 2 examples. One is the famous Bohm-Aharonov effect. And what the Bohm-Aharonov effect is that suppose you have a source of electron and you have a double slit set up and you have some screen, and behind the double slit is a very narrow solenoid with a strong magnetic field going through it, very narrow and long. So that means that the magnetic field is non-zero in the solenoid, but it's 0 outside. However, you can show that for such a configuration of magnetic field, the gauge potential is non-zero outside the solenoid. So in principle, you'd think that the electrons, when they go through the slit, if they were classical particles, they would not see, they will not have, the fact that there's a very localized magnetic field will not have any effect on the electrons, right? But it turns out that at a quantum mechanical level, the wave function of the electron really couples to A rather than B. And when you change the current in the solenoid, your B field outside the solenoid remains the same, but because the magnetic field is changing, inside the solenoid, the A field outside does change. And you can see that there is a shift in the interference pattern here. So your electron does know about changes in A. And this argument comes from an argument of single valuedness of the electron wave function. So the moral of the story is that quantum particles do see A. Now, it's a much more subtle argument to actually show that what they see in A is not just A, but a certain twist in A, a certain topological aspect of A. But that's outside the scope of today's lecture. And the other example that I want to use to motivate using A rather than B are magnetic monopoles. Just because magnetic monopoles have not been observed in nature doesn't mean they cannot exist. In theory, they can exist, and they're perfectly mathematically valid objects. So again, Dirac showed that if magnetic monopoles exist, then the description of an electron in the field of a magnetic monopole actually leads to quantization of the electric charge. Now, this is a big mystery. One of the big mysteries in physics is why is electric charge quantized? And the best explanation we have for that is that somewhere in the known universe, there exists a magnetic monopole. Okay? And also, magnetic monopoles actually arise very naturally in grand unified theory. So our particle physics paradigm, we believe that the standard model probably fits into some bigger theory, a grand unified theory. And if that is so, the magnetic monopoles, even if they're very rare, they should exist in the universe. Maybe not in the observable universe, but somewhere in the universe. Anyway, so yeah, magnetic monopoles, to describe them, you need A. So this is just to motivate why we need A. Okay, how do we derive these? Now let's write down a Lagrangian from which we can derive our Maxwell's equation in the covariant form. The Lagrangian is very simple. It's just this. And you vary this by varying with respect to A and using the Euler-Lagrange equation, which I'm writing just to remind you what it is. I might ask you to write this down in the interviews. If you now plug in what L is and use what the expression for F is in terms of A and do these partial derivatives, then you will find that you get Maxwell's equation. Okay. Some comments. F00 is 0 because F is antisymmetric. So this means that our Lagrangian, L doesn't contain the time derivative of A0. So that means that A0 is not a dynamical field. That if you write down the if you derive the equation of motion for A0 using using this Lagrangian, you will get an equation which doesn't have time derivatives of A. And therefore, that equation would be algebraic. A0 will not be a propagating degrees of freedom. And so you can think of A as a Lagrange multiplier, and therefore, the constraint equation that you actually get, so the equation of motion for A0 that you get is this equation. Of course, you're not going to get a time derivative there. I think, David, do they get something on constraint systems at some point?
Probably in quantum gravity course.
Okay, in quantum gravity, you will see some more about quantization of constraint systems. But so this equation, if you remember the definition of the electric field, is nothing but Gauss's law. Okay. Now that's comment number one. Important observation, let me erase this. if you make a gauge transformation, so that means if you replace a mu by something called a mu prime, which is a mu plus some derivative of some scalar function, then f mu nu of x goes to f mu nu prime. I'm not going to write the x anymore. But that thing doesn't change. And why is that? Because it's f mu nu is an antisymmetric in mu nu, so when you replace a mu by a mu prime, partial derivatives are going to commute, right? But because this is an antisymmetric combination of those guys, the term involving derivative of chi will cancel out. Well, will not contribute. So under this transformation, the field strength remains invariant. And this transformation is called a gauge transformation. In textbooks and in everywhere, this is known as a gauge symmetry. However, this is not a symmetry that we understand. This is not really a symmetry, because if you remember, by symmetry we mean when you change the field in a way where your parameter of change is a constant parameter. Whereas here, the change is parameterized by a function. So this is not a constant parameter, right? If we take chi to be constant, then of course this becomes 0. So because this is not a global symmetry, you cannot apply Noether's theorem to it. Because Noether's theorem is only applicable for global symmetries. And therefore, there is no conserved charge associated to it. And the other thing is that when we make this transformation, the field strength doesn't change. And and for most purposes, it's really the field strength that is the physics. So the physics is not changing. So this gauge symmetry is nothing but a redundancy of our description. Now you might say, hang on, I've just argued that a mu is the fundamental thing to think about. And therefore, why should we care if the field strength doesn't change? A is changing, and therefore the physics should be changing. And there I'm going to go back to that mysterious comment I made that the physics in these cases are really in the twist topological aspect of A. And that topological aspect of A is unchanged whether you're working with A or A prime. You just have to believe me there. And if you want to look up, I encourage you to read more about the Bohm-Aronoff effect. And a good place to look at that, a good, nice, short overview, is the book by Ryder, Louis Ryder's quantum field theory. OK, so the upshot, let me recap. The gauge symmetry means that this transformation has a redundancy in description. You've seen this before in GR. In GR, whenever you made a coordinate transformation, your Riemann tensor, which is actually a kind of field strength, it changed up to some matrices which encoded the fact that you're working in a new coordinate system. In a sense, F is analogous to the Riemann tensor. But when you made the coordinate change in GR, your Christoffel symbols, they were not tensorial object. They did not transform like this. They transformed in a way their one part was tensorial, because this guy had 3 indices, so you get 3 of the transformation matrix. But then you get another part, which is like an inhomogeneous part, right? So I don't exactly remember what that looks like, but let's write this as something chi, and it probably had like 2 lambdas or 2, something like this. And this is analogous to this. See under. So here it's not it's an inhomogeneous transformation, right? When in the next course you will see a generalization of the Maxwell field strength, in which you will actually get these more factors, analog of these factors. Okay. So just keep this in mind, and when you come to the next course, you will see some generalization of that, and you can ask more questions about it to your lecturer. So, if you now think back to your undergraduate magnetism course, at some point, by doing a careful analysis of the equations, you were told that when you're working with A, because of this redundancy of description, you have a choice in choosing what the divergence of A is. So you can actually choose this without changing the physical description. And this choice is called a gate choice. And there are many different gate choices. One popular gate choice is called the Coulomb gauge, which sets the divergence of the 3 vector A to be 0. This treats the space component and the time component differently. So this is a non-covariant gauge. And the other gauge, the gauge that we will be using, is known as the Lorentz gauge. And in this gauge, it is the 4 divergence of A that is 0. So you can write that, if you want to write that in a non-covariant form, you're saying that the divergence of 3 divergence of A is equal to the time derivative of A0. There are other gauges such as I think there's some gauge called the Feynman gauge. I'm not sure. Sometimes it's related to something called a Landau gauge, and it's basically choosing this not to be 0, but proportional to some scalar function. Okay. So, by the way, this Lorentz is not our friend Lorentz or Lorentz transformation. It's a different Lorentz. But it's ironic that the Lorentz gauge is actually Lorentz invariant. So we are going to be quantizing our theory in something that looks like this gauge, but we'll run into some subtleties. David Tong does the quantization in both gauges. So if you're curious about the Coulomb gauge quantization procedure, I suggest you look up David Tong's lecture note. All right, so we are thinking of doing it in the Lorentz gauge. Most textbooks will call it Lorentz gauge with a T. And that's why David Tong says that the guy Lorentz was unfortunate enough to be one letter away from fame or immortality. So this is the Lorentz gauge. So now, if we now plug this into our Maxwell's equation, here you see that this, so let's look at the source free Maxwell's equation. So the right-hand side is 0, no sources, and this is 0 because we are imposing the Lorentz gauge. Then our Maxwell's equation is very simple. And then we can write down some plane wave solutions. And if you plug this into our Maxwell's equation, then we find that this implies that the forward momentum of our plane wave has to be null. K doesn't have to be 0 because we're in Minkowski space-time for this to be true. And then if we now take our ansatz and plug it into the Lorentz gauge condition, then we find that the four polarization components have to be orthogonal to the momentum. Now, one of the interesting things about the Lorentz gauge is that this gauge condition does not fix the gauge completely. You still have some wiggle room for making gauge transformations. So suppose you make another gauge transformation where you add it to this, the chi, the derivative of chi. So as long as chi satisfies this equation, this condition does not change, right? So if you call this a mu prime, then if chi, so if you now, if you replace a mu by a mu prime, then you basically get, you still get the same condition if, if the Laplacian acting on chi is 0. So if you assume this, you're still in the Lorentz gauge. So another way of saying that is that the Lorentz gauge does not fix your gauge degrees of freedom completely. Okay? So using these observations, we can now show that although superficially, there are 4 components. There are the ansatz we took for a mu has 4 polarization components, but only 2 are independent. So, so this means that if chi is going to satisfy this equation, that means chi has the form e to the power minus. We can write it as e to minus ikx, where this k is the same as this k. And because k is null, so if you take apply the D'Alembert on it, because k squared is 0, this equation is satisfied. So using this, you can show, and this is a very easy exercise, is that under a gauge transformation, the polarization vector actually changes to a new polarization vector, which is the old polarization vector time plus some constant that you can choose, k mu. And because you can make this gauge choice, you can make this transformation, you can you can choose the 0th component of your polarization vector to be 0. And once you've done that, this equation then means that you have, so epsilon are 3 vectors now, is a 3 vector now, and this is one constraint, so that cuts it down to 2 degrees of freedom. So by using the gauge symmetry, we can show that although superficially we have 4 polarization states, but physically we have actually only 2. So how do we interpret these gauge fixing conditions? There's a nice geometric interpretation that you will come back to in the QFT2 course in the context of non-abelian gauge theories. So suppose this is the space of all solutions of A. So this is the space of all A's. Okay? So in this space, you will have what are called gauge orbits. So each of these is a gauge orbit. What I mean by gauge orbit is that suppose you have some solution to your Maxwell's equation, say A1, and then I make a gauge transformation, and then it moves to another point, because it's physically the same thing. Let's call it A1 like this. It moves to another point, A1 prime. But it is physically the same thing. So the gauge orbits are the orbits that you move along as you make a gauge transformation. Okay? So suppose you have another physical configuration, say A2, then the gauge transformation will move you along this gauge orbit to another equivalent gauge potential A prime. Yeah?
Is this the same orbit in terms of group action?
It is related, it's not the same thing, because it's, there is an underlying group involved, but the action is not the kind of action that it's not the left action or the right action or the adjoint action that we usually understand because of the inhomogeneous part of it. But it is related, yeah. Okay, so what the gauge fixing conditions do for us is that it chooses a slice through this space. So this is, say, the Lorentz gauge condition. If you take a different gauge fixing condition, such as, say, the Coulomb gauge, you find you're slicing through this space of solution at a different point. So suppose this is the Coulomb gauge. Okay. You can have your own gauge conditions. So the point of the gauge condition is that it picks up one solution, one representative solution from each gauge orbit. Okay. So, yeah?
Is two different gauge completely equivalent, or do they care about boundary conditions? Because if I'm not wrong, Coulomb gauge will make one of your equations some kind of like a elliptic partial differential equations. Like it will be a Laplace equation of sorts.
Right. So you're asking a question about whether the gauge, it should be, it seems, at least superficially, it seems like the different gauge choices should lead to different boundary conditions, right?
Yeah, like you cannot, I'm not sure if given any problem, you can always choose any random gauge you want.
Up to topological considerations, I think you can. I don't have a proof for that, but I think if you're working with certain topological non-trivial solutions such as the monopole and stuff like that, then I think there might be some obstructions in choosing any random gauge. But so if you choose a different gauge, your boundary conditions will look very different, right? But physically, they would mean the same thing. Okay, so that's now you have to go and make that into more mathematical rigorous by yourself. But that's what I'm going to state. So anyway, so this is the interpretation of the gauge fixing condition. So each gauge fixing condition picks out one, a single point from each of the gauge orbit as a representative physical configuration. The Lorentz gauge does not fix your gauge completely, so that means that there is a little bit of fuzziness over here. Okay, let's quantize the theory. So in quantization, I'm going to choose the Lorentz gauge and because the equation of motion in the Lorentz gauge is very simple, and we wrote down the solution as a plane wave, so an arbitrary solution would be a linear combination of those plane waves. So an arbitrary solution would look like there are 4 independent polarizations, so we introduce 4 polarization vectors, and we label each of this polarization vector by lambda, and these are vectors, so there is a space-time vector index on it. And in general, they will depend on the momentum p. And these are the Fourier coefficients. And this is the basis. And then, in principle, if we can have these polarization vectors to be complex, if they're complex because A is real, this has to be the complex conjugate And similarly, the Fourier coefficient also has to be complex conjugate over here, and the plus IP dot x. So this just follows. So now we have 4 polarization vectors. So there is lambda 0, 1, 2, 3. That's how we choose to label them. Not 1, 2, 3, 4, but 0, 1, 2, 3. So the Lorentz gauge condition just tells us that for a given epsilon, for a lambda, this is 0. Now for the spatial components, suppose we can choose something which has a 0 in its time component, and its spatial component, say, is some 3 polarization vector. So I'm giving an example of the possibilities. And we can choose these guys in such a way, E1, E2, such a way that we have EI dotted with the 3-dimensional part of the momentum vector to be 0. Now, we can also choose one of the polarization vectors to be parallel to the momentum vector P. Because if we choose this, then we can see that this is actually satisfied. And we will come back. So in other words, we will come to, when we get to choose a basis for these guys, we will end up choosing a basis in which the time component is non-zero. And if we choose P such that P is, say, 1, 0, 0, 1, so our photon is propagating along the z direction. Another choice could be 0, 0, 0, 1. So these are bases, and the 2 other vectors that we'll choose, can be 2 of these guys. So, the mathematical condition that we impose on the basis vectors this doesn't go up. So I'm just going to go over there because otherwise cover it up. Sorry? So from electromagnetism, your polarization vector can be complex, right? For example, if you're describing circularly polarized beams, then they have to be complex. So we impose the following orthonormality condition on our polarization vectors. So this is the orthonormality condition. And and we also choose the completeness condition. And the completeness condition is this one. they almost look the same, but there's, of course, a subtle difference, right? Mu, nu are space-time indices, whereas lambda, lambda prime are labels. So this is a orthogonality. I would probably say orthogonality than orthonormality because the normalization of some of this vector is not 1. It's actually -1. The mathematicians get really pissed off when you say something is normalized to -1. And this is completeness. Yeah?
Sorry, Cooper, when you have that H and lambda lambda prime, oh, it's contracted with the labels lambda?
Yeah, yeah. Yeah. So note that the Lagrangian that we wrote for our the Maxwell Lagrangian we wrote, now that we have gauge fixed our Maxwell's equation, it no longer gives this equation. So if we are to work with this equation, we have to actually add to our Lagrangian a gauge fixing term. And this becomes important when you are trying to quantize your theory in the path integral formulation. And you will see why that is so in the next course. But I just wanted to tell you that for the sake of completeness. So our electromagnetic Lagrangian was this guy. But we add to it a gauge fixing condition. And for this case, we want to get the gauge fix Maxwell's equation over here. Then if you add this gauge fixing Lagrangian, then your total Lagrangian is so up to some integration by parts. This becomes this is the gauge fixed Lagrangian. So when Freddie taught this course, because you worked with an action which was not the Maxwell action, he called it the non-Maxwell theory. And perhaps there is some justification to saying that. So anyway, if you have this Lagrangian, then if you derive the Euler-Lagrange equation from it, you will get what we want. But for quantization, we also require a conjugate momentum. So what is pi mu? So pi mu, if you compute it, so remember that this is given by something like this, right? And when you compute this, this is 0. Becomes this, right? And now you see that y, yeah?
In the gauge term, we have the divergence of
a squared. Squared? It is, okay.
oh, okay.
Yeah. Sometimes I write 2 like this, which looks like a nu,
Yeah.
It's an old bad habit of mine. Sorry about that. Okay. So now, you can see we have done something very cheeky. By introducing the, gauge fixing term, we now have a pi naught that is actually non-zero. Remember that the original Lagrangian did not have a zero naught, right? But our gauge fixed Lagrangian now, by adding the gauge fixing term, we do have that. And we need that for a quantization, a covariant quantization. So we impose the following covariant quantization condition. So we say A at, so we fix the time, and similarly, this is also true. So these are the equal time commutation relationships. In other words, we are in the Schrödinger picture. And the non-trivial commutation relationship, I'll just write it down. In the lecture notes that I gave out, I think I said anti-commutation at some point, where I meant commutation. There are no anti-commutation in this business. You have to have fermions to be able to do that, so please correct that. Okay. So the non-trivial one, the one which is between A and pi, that is now we impose this to be, we put a minus sign here. And we put the minus sign here so that for the spatial components, we get a positive sign on the right-hand side, which mimics the equal time commutation relationships that we impose on scalar fields. Because if you look at that equation, it just looks like the equation. It is the equation for a massless scalar, for massless scalar particles, right? So you want to have for the spatial part of this to be the same commutation relationship that you would impose, say, on a massless scalar particle. So you can then define what the Feynman propagator is. And now the Feynman propagator will be a tensor. And you define that to be A mu x, A nu y. The time ordering is the same because you're describing with bosons. But the Feynman propagator is a gauge-dependent quantity. So it's gauge-dependent. And this actually comes to the heart of why we do gauge fixing. You will see in QFT2 there will be a tutorial problem in which you will try to write down the Feynman propagator without fixing the gauge. And then you will see that it's a singular object. It doesn't exist. Because the Feynman propagator is the inverse of the wave function, sorry, of the wave operator. And you will see that if you don't fix the gauge, the Feynman propagator doesn't exist. And if it doesn't exist, you can't do any calculations. So we can think of this as the massless limit, in this case, of, so you can calculate this, of the propagator of a scalar field. So this is a propagator for a scalar field. You take the m to 0 in it, and you multiply it by minus eta mu nu. So the expression for this is as you would expect, the familiar, but now you don't have a mass anymore. Right. So what are the commutation relationships on Fourier space? Well, as you would guess, I think I wrote the A lambda with upstairs, so now I'm writing it downstairs. And I don't mean like lowering the index. So this is not like A lambda is not like eta lambda lambda prime A lambda. I think it's the same thing. Okay, I'll just try to be consistent, but and also I'm going to drop the bracket around it. You just have to remember that there are labels. So this becomes and then the other ones are AA okay. So there's something disturbing about this equation, and the disturbing thing is that if you try to create a state out of the vacuum using A0 creation operator, then you can compute, if you assume that your vacuum is normalized, then by using this equation you find that the norm of phi is negative. There's some delta, but okay. And that comes from the fact that you've got eta 0, 0 over here. So what have we done wrong? So we basically haven't carefully analyzed how to impose our Lorentz gauge condition. And it turns out that this condition you cannot impose as an operator condition. If you try to impose this as an operator condition, it's too strong, and you get inconsistencies. And the way to see it is to say, okay, if you calculate the covariant commutation relationships, so these are not equal time commutation relationships, you can just go ahead and compute that. You can show that this is proportional to this is the Feynman propagator. Now, if you take the divergence of each side with respect to the x, then you get over here Now, if we impose this as an operator equation, then the left-hand side would be 0. But by taking the expression for D and computing the right-hand side, you will see it is not 0. So you get a contradiction. So we have to be a lot more clever in imposing this condition. And we will see that when we impose that condition, these states will not contribute to physically measurable quantities. So the way that this is imposed is it's imposed as a constraint on the space of states. And I don't want to call it the Hilbert space, because Hilbert space do not have negative norm states in them. So the state space is much bigger than the physical state space. So we impose that for if this is a physical state, then it has to satisfy this condition. It has to be annihilated by this operator, where A mu plus is that part of A that contains the annihilation operator. So this is A plus, A mu plus. And there should be a mu somewhere. Okay. So if we impose this, then what if we take the Hermitian conjugate of this? Then the Hermitian conjugate is this guy. So this actually is implied by this. And what if we now compute this thing, then we can decompose this in terms of the plus part and the minus part. And the plus part will kill this one, and the minus part will kill this one. So we have this equals to 0. So the Lorentz gauge condition is imposed as an average, as an expectation value for the physical state. But you don't have to impose even that strong a condition. You can just impose the weakest thing you can think of, and that thing follows. So now let's take a case where the polarization P is along the z-axis. Okay, so this is an example. And let us choose our 4 polarization vectors in the following way. There is one which is, so this is a time-like. So in other words, whenever we have A0 dagger acting on some state, it'll create a state which has that polarization. And then we have 3 space-like polarization. Let's choose, say, this to be 1 along the x-axis, and this to lie along the y-axis, and then this would be along the z-axis. just note that our direction of propagation is also along the z-axis. And then ask, what does this condition imply? So if you now plug in these values in here, then that condition implies that the 3-component minus the 0th component acting on your physical state psi is 0. So let's see what it gives us for something that we can compute physically, such as say the Hamiltonian. So before we can evaluate what the energy of a physical state is and see whether our polarization, such as the bad polarization, the time-like polarization, and the longitudinal polarization that we don't expect to see. So this is longitudinal. We want to see whether those guys contribute to the energy of a state. So the Hamiltonian is d cubed x normal ordered pi mu a mu minus the Lagrangian density. And when you calculate this, it's minus d cubed of k divided by 2 pi cubed half summed over all the polarization a lambda dagger, a lambda number operator. Let's put a p here, and then summed over that. And because the trace of this guy is negative, well, we need the minus sign for this to be positive. So, and then we take our state, which satisfies this condition, and we compute what this is. Then we see that because of this condition, the contribution from the longitudinal part, the 0 part and the 3 part, they cancel out. And that in the end, what you get is just summed over the 1 and 2 part. The contribution is just from the physical polarizations that you would expect from your classical intuition. And so if you're not convinced, let me show you that this is actually the case by showing that the part that I'm claiming is 0 is actually 0. So it's just that part is the number operator from the A0 part. And there's a minus sign which comes in because of this eta. And so it's a 3 part, and they have momentum arguments. Okay, and so you can write this as A0 dagger A0 minus A3 dagger A0 plus A3 dagger A0 minus A3 dagger A3. So I'm doing very simple algebra, but it's worth doing. And then we can write this as A0 dagger minus A3 dagger times A0 plus A3 dagger, A0 minus A3 acting on psi. So this thing is 0, and this thing is 0, meaning that this whole thing is 0. Okay. So we see that covariant quantization involves working with a much bigger space of states in which you have both longitudinal polarization and time-like polarization. But imposing this condition on physical states imply that those polarizations do not contribute to physically measurable quantities. I think in the tutorial we'll see an example where longitudinal polarization actually, the unphysical polarization states actually even don't contribute to the Feynman diagrams when you sum over all the Feynman diagrams at a given order. Okay, so I'll end there. And you are 10 minutes early, so.
So here just consider the longitudinal part of the Hamiltonian. What happened with the transverse part?
Oh, the transverse part is this. It's only sum over 1 and 2. It is the transverse part which contributes.
Okay.
The point is that the longitudinal part cancels the time-like part. So, I mean, we have all 4 components, but this condition is very clever that it eliminates, it cancels the unphysical components cancel against each other. But so this is kind of, there's another way of doing this, this thing in the Coulomb gauge, and you can look at David Tom's notes, and he does it. But the price you pay is that there's no manifest covariance in Coulomb gauge. Now, this is just a formula. We don't really use a lot of it, and it's written competitiveness, even less so. But it's good to see once in a while. Yeah?
So this is different from canonical quantization.
No, this is canonical quantization, but in a gauge that is covariant. And therefore, you have to deal with a bigger state space than the physical space. If you were doing canonical quantization using Coulomb gauge, then you would not have all these worries, because you would be working with two degrees of freedom all along, and you'd be fine. But then your Hamiltonian will have forms, will have a form which is not
manifestly covariant.
well, not your equations. I mean, Hamiltonian at the end of the day is not covariant anyway. So. Right.